All right, now there is a fifth operation, and that's this little circly guy here. It's called function composition. And what it means is you take one function and plug it into the other function. It's where you take the output of one function and put it into the input of another. So imagine each function represents a process, and imagine you wanted to do like an assembly line. You know, on an assembly line where you have some conveyor belts, and they take your objects into machines, and then the machine changes the object somehow, goes out the other side of the machine, out onto the exit conveyor belt, right? On an assembly line. Let's say you have two machines in a row that you want to manipulate the thing you're manufacturing. And let's call the second one F and the first one G. So these machines are functions. If I put X onto my assembly line, then when that comes out of G, G is going to be the function that's going to turn it into, G of X. And then we're going to take that output and run that straight into the machine F, and out the other side is going to come F of G of X. So that's what goes here, F of G of X. We're going to write this as either like this or like this. So this fifth operation is composition, and we pronounce it of, and it's defined like this. Whoops, god damn it. So I would read this, this is a little goofy, but I would read this, F of G of X is the same as F of G of X. Make sense? Come on now. You have to get it just right. So I had these example functions, yeah? Let's say I wanted to know what is, let's evaluate first. What is F of G of 2? The way I would get that is it's F of G of 2. So I'll say, first I'll plug 2 into G. That's 2 squared minus 4, minus 4 times 2. So that's 4 minus 8 is negative 4. So G of 2 is negative 4. So it's like I took a 2 here, plugged it into G, and G pumped out a negative 4, like so. So now I'm going to take negative 4 and stick that in F. F of negative 4 is just 2 times negative 4. Plug that in here. So this is negative 8. So F of G of 2 is negative 8. So that's how you do function composition. Goofy thing is, if I wanted, Jesus, come on. If I wanted G of F of 2, so I could also write that Goff, G of F of 2, right? Then first I'm going to do F of 2 is 4, yeah? Because it's 2 times 2. And then G of 4 is 4 squared minus 4 times 4, so that's 0. So G of F of 2 is 0. So it's a different answer. Order matters. If you plug your thing into G first and then F, you'll get one answer. If you do F first and then G, it's a different assembly line. It's going to make you a different finished product. So you can't just switch the order of these. Order is important. Let's do a couple more. How about what is, let's see, what is hog of 6? So that's going to be H, oops, already wrote that, of of g of 6? Well, first I'd need to do g of 6, and that's 6 squared minus 4 times 6, which is 12. And then I would do h of 12. So that's the square root of 12 minus 2, which is root 10. So h of g of 6 is root 10. Just for the heck of it, g of h of 6, well, first I plug 6 into h. That's the square root of 6 minus 2, right? So that's root 4 is 2. And so now I take that 2 and I plug it into g. G of 2 is 2 squared minus 4 times 2. Well, that's negative 4. I think I already did that some. Oh yeah, I did already do that here. So g of h of 6 is negative 4. So order matters is the point I'm trying to make. Now, let's find some formulas, right? I'm getting better at this finger command here. Let's find an algorithm for, how about fog, f of g of x? Well, that's f of g, oops. So now I'm going to try to find a formula. This is a little bit of work. What I need to do is take g of x and plug that whole thing into f. So I can write that like this. I'm going to take g of x here, and I'm going to plug it in to f up here. So that means where this x was, a g of x is going to go. So this is 2 times g of x. You see how I evaluated this, but at this expression? So it's 2 times this guy. Now, I'm going to do one more substitution. Since I know that these are equal, I'm going to substitute that whole formula in for g of x. So now this looks like 2 times g of x is x squared minus 4x. And all I have to do is distribute 2x squared minus 8x. So that's the formula for f of g of x. Let's say our next problem is find g of h of x. So that's equal to g of h of x. So I'm going to take this h of x and plug it in to g. So it's going to go where each of these x's is, up here. So g of h of x is equal to, h of x squared minus 4 times h of x. So everywhere that there was an x, I put an h of x, and just to be safe, I put it in parentheses. Now, instead of putting the name h of x, I'm actually going to put the formula for h of x, which is root x minus 2. Sorry, just a moment here. So the formula was root x minus 2, like so. And now I can simplify just a little bit. The square root of x minus 2 squared, those cancel each other out, and that's just x minus 2. So that's the formula for g of h of x. Make sense? We put one formula into the other formula, and we got our answer. And that's because you're allowed to evaluate functions at expressions. That's what we're doing here. Okay. Finally, so that's how to make the formula. Try doing h of f of x on your own just to make sure you've got it. So this is the square root of f of x minus 2. And f of x was 2x, so this is the square root of 2x minus 2. Okay. We've saved the best for last. How do I find the domain of this thing? I want to go back to this assembly line analogy. Now this is a little confusing. X goes into G first and then F, don't forget, because this is the same as f of G of X. It's easier when you write it this way. So I'm going to plug X into G first. So X goes into G, and then out comes G of X. G of X goes into F, and out comes f of G of X. So it's a two-part process, and at each of these parts, I can't have a failure. So X has to go into G of X. This is the first possible point of failure. What this is telling me is if X goes into this machine, then X is in the domain of G. Then the output of G is going to go into the F machine. So what that's telling us is that G of X, this expression, must be in the domain of F. So those are my two rules. It's easier to remember if you draw the picture. First, to be able to plug X into G of X, then I have to be able to plug that whole thing into F. So this is pretty tricky. Let's do an example to make sure we've got it down. Let's say that m of x is equal to 1 over x minus 5. And let's say that p of x is the square root of x minus 2. I like this one. What is the domain of mop of x? M of p of x. So that's the same as mop of x is the same as m of p of x, which is where I take p of x and I plug it into m. So that's 1 over p of x minus 5, or written entirely in formulas, 1 over root x minus 2, now n the square root, and that's all minus 5. So that's the formula, but what's the domain? First, x has to go into p. And we already said p is the same as h from before. The only numbers that can do this are 2 or bigger. If I put in a number smaller than 2, I'm taking the square root of a negative, and that's not allowed. So first rule, x has to go into p. That means x is 2 or bigger. Now the second thing that happens is x came out of p, and we got p of x. And now that whole thing has to go into m. So this is going to take a little deciphering. P of x must go into m. What's the domain of m? What can't I plug in here? 1 over x minus 5. I cannot divide by 0. So x minus 5 can't be 0. X cannot be 5. The domain of m is every number except for 5. So if I say p of x must go into m, what that means is p of x cannot be 5. Not x can't be 5, but p of x. It came out of the first machine here. And now I'm saying if I got 5 out of the first machine, then I'm stuck trying to get into the second machine. Let's take a look. P of x was the square root of x minus 2. So this is going to tell me root x minus 2 cannot be 5. I'll go ahead and square both sides. X minus 2 cannot be 25. So I just multiplied each side by itself. And then I can add 2. Turns out x cannot be 27. So let's take a look here now. I got x can't be 27. So first x has to go into p. So if I plug in 1, I'm going to get the square root of -1, and that's I, and that's no good because I don't want imaginary outputs in this chapter. These are real valued functions. So that's not going to work. That's going to fall out right away. If I plug in a 1, it goes into G, and, well, it doesn't go into G. If I plug in 6, though, the square root of 6 minus 2, 6 goes straight in. Square root of 6 minus 2 is 2. So if I put a 6 in here, that's going to turn into a 2, and then f of 2 is 1 over 2 minus 5, that's -1/3. So 6 goes all the way through. First it turns into 2, and then it turns into -1/3. But there's another failure mode. If I plug in, the number I got was 27. If I plug in 27 into G, or into P, rather, P of 27 is the square root of 27 minus 2. So that's the square root of 25, which is 5. So P of 27 makes a 5, and f of 5 doesn't work. So any number smaller than 2 won't go into the first one. 27 specifically will make an output that won't go into the second one. So it's a little bit of a tricky way of thinking. I can plug 5 in at the beginning. If I plug 5 in at the beginning, I'll get the square root of 3, and then I'll get 1 over root 3 minus 5. That's just fine. I have to make sure I don't plug anything into G that'll manufacture something that breaks F. And that's the way it is. So the domain of mop is any number bigger than 2, but not 27. Like so. Well, if that's all crystal clear, let me do one more of these, just in case. Let's say that k of x is x over x minus 2. And let's say m of x is 6 over x squared minus 1. I want the formula and the domain for k of m of x. This is a tricky problem, but we're up to the task. So this means x goes into m, and then that answer goes into k. So first I'm going to try to find the formula. That means this is k of m of x. So I'm going to take m, and I'm going to plug it in wherever x was in the definition of k, here and here. So k of m of x is m of x over m of x minus 2. This is a nice intermediate stage. Do these things one at a time, because now I'm going to take this definition of m, this formula for m, and replace the literals of m with it. So m was 6 over x squared minus 1, and m was 6 over x squared minus 1. So the only thing that's changed is that each of these, we replaced the name of m with the algorithm for m. So it's the same expression, just with m replaced. And now, this day, we have the task of simplifying the monster. Okay. A few different ways to do this. I'm going to go ahead and let me simplify the denominator first. Maybe if I can simplify the denominator, I'll get something good. So this division sign is splitting our problem into two parts. Numerator's already simplified, denominator's not. I want a common, I'm going to take 6 over x squared minus 1 minus 2, and I'm going to get a common denominator. Oops. So this is 6 minus 2 times x squared minus 1 over x squared minus 1. Capiche? That's a little better. Let me simplify the numerator. This is 6 minus 2x squared plus 2 over x squared minus 1. So this is 8 minus x squared over x squared minus 1. Oh, sorry, 8 minus 2x squared. My bad. So that's this denominator. So now I can rewrite k of m of x. Top is unchanged. Bottom is this. So when you have a giant assembly like this, it's cool to, my strategy was take this giant assembly, pull one component out, and manipulate the component into something simpler, and then put it back into the assembly when I'm done. So now I've got a 4-part fraction where each of the parts is simplified, and what that lets me do is say this giant division sign in the middle, this giant fraction sign, it's literally a division sign. So it's saying take the top and divide it by the bottom. I keep writing the wrong thing. So take the top, divide it by the bottom like so. But we know a strategy for doing that is keep, change, flip. So this is really the same as, I want more space over here. So this is really the same as first one we keep. The division changes to multiplication, and we flip the second. At this point, I think it's painfully obvious what cancels. It's these factors, like so. X squared minus 1 on top, x squared minus 1 on the bottom. So all we're left with is 6 over 8 minus 2x squared. All three of those have a common factor of 2. I can factor 2 out of the top and get 3. I can factor 2 out of the bottom and get 4 minus x squared. So that is the simplest way to write k of m of x. A lot better than what we started with, don't you think? So there's my formula. And just looking at the formula, I know that if x is 2 or negative 2, that this is going to be dividing by 0. So I know that 2 and negative 2 aren't going to be in the domain. But it's a little more complicated than that. The domain isn't just the things we see by looking at this formula. No, the domain is how can I reasonably construct this whole function. So to get this whole function, first x goes into m, and then that answer, m of x, goes into k. And that's how we get com of x. So I have to be able to do the first step and the second step. Again, m of x was 6 over x squared minus 1. and k of x was x over x minus 2. Make a little table here. What's the domain of m? I cannot divide by 0. X squared minus 1 is 0 whenever x is positive 1 or negative 1, right? A positive 1 would make that 0, a negative 1 would make that 0, nothing else will. You can see that quickly by factoring it, x plus 1, x minus 1. So the domain of m is every number except for 1 and negative 1. So what's the domain of k? I think you can see. If x is a 2, we're dividing by 0. Otherwise, we're fine. So the domain of k is x is not 2. But how does that help us with this problem? Well, it's an important step. How that helps us is, now I can say, okay, if x is going to go into m, then first off, I can't have 1 and I can't have negative 1. Second, m has to go in a. So if x is going to go into m, we have to follow these rules. Now m of x has to go into k, which means m of x will break k if we try to plug in a 2. So m of x is not 2. So the first part, the original input can't be 1 or negative 1. And the intermediate step, we can't have a 2 in the middle because that'll break k. So when am I going to get a 2 in the middle? Let's find out. M of x can't be 2. What's the formula for m? It's 6 over x squared minus 1. And that's can't be 2. I'm going to go ahead and change up this fraction here. I've done this before, but remember, if I have a over b equals c, I can multiply both sides by b to get a equals bc, and then I can divide both sides by c to get a over c equals b. So that's the trick I'm going to use right here. So all that's actually happened is the denominator and the far side have changed places. See, b and c changed places, a stayed put. So I'm going to use those 3 steps here and say 6 over 2 can't be the same as x squared minus 1. Well, of course, that means 3 is not x squared minus 1. That means 4 can't be x squared. And that means x cannot be 2 or negative 2. We'd put a plus or minus here. So x can't be 2 or negative 2. If it is, I'll get a 2 when I plug it into m, and that'll break k. So in the end, there are 4 numbers that break the process. If I plug in a 1 or a negative 1, it breaks m. If I plug in a 2 or a negative 2, it goes into m just fine. So m of 2 is 6 over 4 minus 1. That's 6 over 3, which is 2. 6 over m of negative 2 is 6 over negative 2 squared minus 1, which is also positive 2. So if I plug in either of these numbers, they go into m just fine, but they produce a 2, which breaks k. So my domain is any number except for negative 1, negative 2, positive 1, or positive 2. Whoops, negative 2, negative 1, positive 1, positive 2. Which leads to the worst expression you'll ever see in interval notation in this class. Domain of k of m. If I wanted to write this in interval notation, I could say, as an inequality, it's easy. I could just say x is not plus or minus 1 or plus or minus 2. In interval notation, it's terrible because there are 5 chunks to this interval. So first chunk here, negative infinity up to negative 2. Second chunk, negative 2 to negative 1. That's here. Third chunk, negative 1 to 1. Fourth chunk, 1 to 2. Fifth chunk, 2 and on up. I'm only showing you this because sometimes my open math or one of the tests will demand interval notation. If you're working this on your own time for practice, inequality notation is probably better here. All right, that is it for 3.4. Thank you for joining me.